Hi everyone, welcome back. In this video, we are going to discuss the Wacker oxidation or the Wacker process as it's called. This is an organometallic reaction. In fact, it was one of the first industrially applicable organometallic processes. And what this reaction does is it uses a catalyst. So there's a palladium catalyst that's used along with other components here. But the primary reaction that's going on here is the conversion of an alkene. So this reaction can convert an alkene into a carbonyl compound. Now, the regiochemistry of this reaction, it follows a Markov-Nikov sort of an addition, although anti-Markov-Nikov variations have been developed, but traditionally, or more classically, it follows a Markov-Nikov sort of an addition. And so the product that's obtained is usually a ketone. So if we start with an alkene, a substituted alkene, a monosubstituted alkene, we're going to make the ketone product. Now, like I mentioned, this was one of the first organometallic reactions to be applied industrially. So what this was used for is converting ethylene into acetaldehyde. So you could make acetaldehyde from ethylene using the Wacker process. Okay, so that was the big industrial application of this reaction, the Wacker oxidation. Now, like I mentioned before, the catalyst here is a palladium catalyst, and additionally, you need to notice copper. So copper, as we will see in the mechanism, it's used for oxidizing the palladium catalyst. So during the reaction, the palladium gets reduced, and so the copper is used to reoxidize that palladium. And oxygen, atmospheric oxygen, serves as a terminal oxygen because when the copper reduces, when the copper oxidizes the palladium, it itself gets reduced. And the oxygen helps to oxidize the copper back to its oxidation state. So the catalyst we're using here is a palladium 2 chloride. So palladium is in a +2 oxidation state. The copper here is also a copper 2 chloride. So it's in a +2 oxidation state. They both get reduced during the reaction, and the oxygen serves to oxidize copper, which in turn helps oxidize the palladium. And we're going to see this during the mechanism. Now, I do want to mention that this is an organometallic reaction, and there has been a lot of discussion about what the actual mechanism of the reaction is. So there have been different schools of thought which propagate or which propose or which favor like one mechanism over another, and I don't think we have a common ground yet. So there are a lot of variables here, and I would point out some of those things as we go through the mechanism. So let's get started with the mechanism. Okay. So mechanistically, it is believed that you start with this palladium 2 chloride. Okay, we have 2 chloride. So palladium is in a +2 oxidation state here. And this picks up chloride. So under the reaction conditions, because the reaction's done in an aqueous medium, so under those reaction conditions, the palladium chloride, it picks up 2 chloride ions to produce a tetrachloroethylene palladate. So this is palladium with 4 chlorines attached to it, a tetrachloropalladate intermediate. And this is what initiates the reaction. So this is what the palladium exists as under the reaction conditions. So from here, now, one of the first steps after this is the olefin coordination. So once we've made this tetrachloropalladate intermediate, and actually before we go into that, let me point out that in this tetrachloropalladium or the palladate intermediate, the palladium is still in a +2 oxidation state. So there's no change in the oxidation state yet. And for those of you who are familiar with organometallic chemistry, this is, you could count the number of electrons. So palladium 2 is D8. The 4 chloride ions, they all bring in 2 electrons each, or contribute 2 electrons to the electron count. So this is a 16 electron intermediate at this point, and that's totally fine for palladium in a +2 oxidation state. 16 electron is perfectly okay. Although you learn about the 18 electron rule, but it does not apply to like all metals in all geometries and oxidation states. So for palladium in a +2 oxidation state, 16 electron is great. So from here, our olefin or the alkene that kicks in, and now as the alkene comes in, okay, as the alkene comes in, it is going to displace one of the chlorides. So this is an alkene coordination or the olefin coordination. So as it comes in, it will displace one of the chloride ions. Now I'm not going into the mechanism of that, but for a 16 electron species like this, you could imagine an associative mechanism as well as a dissociative mechanism. Again, for those who know organometallic chemistry. So if it's an associative mechanism, the alkene could coordinate and then a chloride would leave, or a chloride would leave and then the alkene would coordinate. That's the dissociative mechanism. So let's go ahead and draw the product, the resulting product here. So by the end of this coordination, we'll have the palladium with 3 chlorines now. Sorry, this is a wedge. I'm trying to show a square planar environment around that palladium, and we have our alkene that's coordinated to the palladium. And this species overall is a 1 negative, okay? It is still a 16 electron intermediate. Palladium is still in a +2 oxidation state, but the charge on the overall complex now drops by 1 negative. So because we kicked out a Cl minus, okay, so that brings out this charge, that brings down that charge. So now we are at a 1 minus because the palladium is 2 plus and each chlorine is 1 negative. The olefin itself is not contributing to the charge. It is a neutral molecule. Another thing that I want you to notice here is the mode of binding, okay, how the olefin binds to that palladium. What I'm trying to show here is the palladium coordinating to this pi bond, okay? So if I were to draw this a little bit more appropriately, maybe, I think what I'm trying to say is something like that. So the palladium is actually bound to both carbons. It's bound to the pi bond, which is there between the 2 carbons that are part of this double bond system. Okay, and this mode of coordination again is called an eta 2. So we say that the olefin is bound in an eta 2 fashion because it is using two of its carbon atoms, or the electrons from two of its carbon atoms, to bind with the palladium. Okay, so that's called an eta-2 coordination mode. Now, after this, we get another ligand exchange where a water molecule, which is there, which is the solvent, sort of, okay, because all of this is being done in an aqueous medium, so that's sort of our solvent here. So water molecule kicks out another chloride. Okay, that brings us to a new intermediate here. We have two chlorines, have a water molecule, and we have the olefin coordinated to the palladium. Okay, we have the olefin coordinated to the palladium. Now, a lot of these processes, I also want you to realize that a lot of these processes are reversible, okay, because say, for example, the olefin can bind, but it can also detach. That means this is going back at the same time. Similarly here, the water can coordinate, but it can also detach, so that's going back. So microscopically, like, every step is reversible. So all of these processes, we're going to say that they have some degree of reversibility to them, some more than the others, okay? So we get to the species. Now, at this point, notice that since we kicked out another chloride, the palladium is still in a +2 oxidation state, so it is palladium 2, but there is no charge overall on this intermediate because another chloride just got kicked out. So we have the water. Now, from here, in some places, you might see that there is a loss of proton shown along with this step. So you might see the water written, or you might see an intermediate which is a hydroxyl group or a hydroxide that's bound to the palladium. So you might see this intermediate drawn in some examples or some resources that you're looking at. Now, either one of them is fine, because what they're implying here is that in this step, as the water coordinates, there is a loss of HCl, which does not happen in one step. So it is probably it is a multi-step process there. Okay, because what you can realize, what you should realize is that when the water coordinates to this palladium, because the palladium is electrophilic, it has a 2+ charge on it, that's going to change the pKa of the water significantly. It's going to bring it down. Okay, so the water molecule, or the protons on the water molecule, are going to be significantly more acidic, and so then they can be deprotonated by a base which is in your system. It could be another water molecule, because that's your solvent, so there's an excess of your solvent, so it could be another water molecule, it could be chloride, but you could show it as an HCl. So either one is fine here. And what we will do is we will just use this one here, okay, to continue. Okay, so what I've done is I'm basically going to keep this hydroxide version where we've eliminated an HCl. I'm going to actually move this structure a little bit here to make room for everything else that we have to do. So we're going to say that when this process happens, we are liberating HCl overall. So we get palladium with chlorine. We've got a hydroxyl group on it. And we have the alkene. Okay. Now, once we are at this point, this is where a lot of mechanistic differences have been noted by people who are researching the mechanism of this field, because there are some schools of thought which propose that at this point, continuing on to the next step, okay, between here and the next step, the hydroxide, which is on the palladium, it can internally add to the alkene, or in other words, to put it in organometallic terms, the olefin inserts itself into this palladium hydroxide bond. So that inserts into the palladium hydroxyl bond, and and then another water molecule comes and takes this fills in one of the coordination spots around the palladium. Other schools of thought believe that, again, depending on the conditions, actually, that is what it is believed to be. So depending on the conditions, you could have an external water molecule come and attack the alkene, and this hydroxyl just stays where it is. Okay, so there are some differences in terms of what actually happens. So we are going to skip that part, but I just wanted to mention that. But I'm going to show you what is it that you get. So by the end of this, once the insertion happens, and this is a 1,2 insertion that's happening here. So it's a 1,2 insertion. I'll get to what that means. Okay, because of the 1,2 insertion, we will get palladium with 2 chlorines. We'll get a water molecule, and we are going to have so actually here, so at this point, I think I want to talk a little bit about where does the hydroxyl or the water attack, either ways. Like, let's say if the insertion happens, where would the hydroxyl go? Or if it is the water attacking, where would we attack? Okay, so we have 2 carbons here that are part of this double bond, which is coordinated to the palladium center again. And now again, over here, what I want you to understand is the coordination to the palladium. That changes the reactivity of this pi bond, okay? And olefin, like an alkene in general, okay, this is an electron-rich system. So it likes to add electrophiles to it, or it would behave as a nucleophile, and it would donate electrons to electrophilic species. But if we look at this step here, we have an alkene, and whether it's a hydroxide or it's a water molecule from outside, it almost seems like a nucleophile reacting with another nucleophile. And that's where the palladium comes into play. You know, that's where the palladium does its role. So the palladium being electrophilic, it actually pulls away electron density from that alkene and makes these carbons electrophilic in nature. They have some sort of a partial positive charge to them, like a del positive. Now that partial positive charge is going to be more pronounced at the secondary carbon, okay? This carbon here, which is secondary in nature compared to the terminal carbon, which is primary in nature. And that's because primary or secondary carbocations are more stable compared to primary carbocations. Okay, so because of that reason, the secondary carbon here, the internal carbon, is going to have a more pronounced partial positive charge. And what that implies is the attack of the nucleophile, whether it's an insertion or whether it's the attack by the water molecule, whichever pathway it follows, it is going to happen at this secondary carbon atom. That's where the attack would happen. And so if the hydroxyl attacks the secondary carbon atom, the primary carbon atom would now get will become attached to the palladium center. So that's that's called a 1-2 insertion, and I will go over that again but let me draw the structure that we get. So because of that 1-2 insertion, we're going to get a structure like this. Okay, we're going to get this structure. So this was our primary carbon, this was our secondary carbon, and the hydroxyl group, or the hydroxyl from the water molecule, they become attached to this secondary carbon. The primary carbon is connected to the palladium center. So now I mentioned that this is called a 1-2 insertion reaction, or a 1-2 insertion step. And 1-2 insertions happen when your ligand is bound to the metal center in an eta-2 fashion. So whenever you have a ligand that's coordinated to the metal center in an eta-2 fashion, a 1-2 insertion happens. And what that means is, if you assume that it is actually an insertion and the alkene inserts into this palladium hydroxyl bond, then we can see that you could number these carbons as, let's say, 1 and 2. And when the alkene inserts, it makes bonds at both carbon atoms 1 and 2. So it's inserting, or the addition is happening at both of those carbon atoms. Now, there are other systems, for example, carbon monoxide, which binds using eta-1 coordination mode to metals. It would form bridges. It can behave as a bridging ligand between two metal centers. And in that instance, when it's an eta-1 coordination between metal centers, it would give you a 1-1 insertion. Or even for like a single metal center, carbon monoxide, it would give you a 1-1 insertion reaction. So that is something that's noticed when carbon monoxide inserts into metal carbon or metal hydrogen bonds. But since olefins bind to metals in an eta-2 fashion, they result in a 1-2 insertion. Okay, that is the product that we get. Okay, so we have the 1-2 insertion reaction here, or the 1-2 insertion step, which results in this metal carbon bond now. So this is more of a sigma bond now. Now, from here, the next step is called a beta hydride elimination. And the beta hydride elimination in some way is just the reverse of this 1-2 insertion. Okay, and so what happens in the beta hydride elimination is, when you count from your metal, the carbon that's directly connected to the metal, this is called the alpha carbon. The carbon next over is the beta carbon. If your beta carbon has a hydrogen on it, which this beta carbon does have, okay, then you get a beta hydride elimination with electrophilic metals. And what happens here is essentially that hydride, or the hydrogen with the electrons in that bond, transfers to that metal center. Okay, so that's the electron push over there. And at the same time, the bond between the metal and the alpha carbon goes to the space between alpha and beta there. And so what we get is, we get an intermediate where now we have palladium, we have chlorines, okay, and we have a hydride that's connected to the palladium now, because those electrons ended up on the palladium. And we get this species here with a pi bond between your alpha and beta carbons based on this structure, and the palladium is again coordinated to that double bond in an eta 2 fashion. Okay, I wanted to mention something here that I missed, which is when we get to this hydroxyl intermediate, the overall charge here is 1 negative. When we are at this this palladium alkyl sort of an intermediate, the overall charge is again 1 negative. Palladium throughout these steps, it continues to be in a palladium 2 oxidation state. So there's no change to the oxidation state of palladium yet. Okay, it is still in a +2 oxidation state. And so it is a palladium 2 over here, and there is an overall 1 negative charge here. Now, at this point, I also want to mention something else, which is some of the resources, they seem to suggest that this enol, okay, going back to organic chemistry, this looks like an enol intermediate. So some resources seem to suggest that this enol comes off the palladium at this point and then tautomerizes to the ketone product. Sorry, the ketone product's not on the board here, but that is our final product, and I'll show you what I'm saying here. Okay, so some resources seem to suggest that the enol basically comes off, it just detaches. So like ligands, so it is a very dynamic environment around the metal. Under these reaction conditions, things can basically come on and get off. Okay, so things don't have to basically stick around on the metal like we are drawing them here all the time. Okay, so the enol, once this is formed, it can dissociate from the palladium center, and then since the reaction condition is going to be acidic under these conditions, it can tautomerize to the ketone product. But that's not true because mechanistic studies on these reactions, on this reaction, they suggest that all the hydrogens in our product, they come from the alkene, the starting alkene. There is no other hydrogen that is on our product, which would not be true if there was a keto-enol tautomerism. Because if there were a keto-enol tautomerism step involved, then at least one hydrogen in your product should come from a solvent. Okay, so that has been proved that there is no enol dissociating and then keto-enol tautomerism happening. Instead, what happens here is at this point, there's another insertion. So we have a hydride here, okay, and we have this alkene here, and again, this is eta 2. So what happens is there's another 1,2 insertion step. There is a 1,2 insertion that happens. So this is a 1,2 insertion that happens here. And this leads us to a palladium intermediate where we have 2 chlorines. And the hydride inserts into the palladium. Now, this step can be facilitated by a water molecule. So it is possible that, like your solvent, so it is possible that a water molecule can come in and it just coordinates to the palladium to fill the coordination sphere. Or it does not have to, because our palladium is 16 electron here. 14 electron palladium can survive through catalytic cycles, or in fact, species are known where there are 14 electron intermediates. Okay, so but let's say a water molecule comes in. So there is a water getting in here. Okay, that comes in, which is attached to the palladium here, and that will give us a new intermediate where we have R methyl and then the hydroxyl group. I'm going to draw this slightly differently. In fact, a little bit better because I want to show the next step here. So we have methyl group, we have R. So essentially what's happening here is, again, this alkene inserts into this palladium hydrogen bond. So the hydride is going on this terminal carbon, and the palladium is getting connected to that carbon. So that gives us a new intermediate here. So we've converted this CH2 into a methyl group. Palladium is now connected to that carbon. Okay, and from here, I'm kind of running out of space almost. So I'll probably go into this space a little bit here. So from here, we get another. In fact, I forgot to write what the step was here. This is a beta hydride elimination. Okay, so we go through another beta hydride elimination. And again, you can identify your beta hydrogen. There are two beta hydrogens here, actually. Okay, so from the palladium, we have alpha carbon there. Okay, that's an alpha carbon. This here is an alpha carbon. And we have a methyl here. So that is a beta carbon. So there are hydrogens on that carbon would be beta hydrogens. We have oxygen here. That would be beta to that palladium, and this hydrogen is also a beta hydrogen. And now thermodynamically, the formation of that carbon-oxygen double bond is more favored. It's a stronger bond that's being formed. Okay, so this is a beta hydrogen, and so pretty much the same thing happens in a beta hydride elimination. So this hydrogen is going to come, bring its electrons, get on the palladium. The bond between the palladium and the alpha carbon goes into the space between the alpha carbon and the oxygen. So that would give us a double bond over there. And while this is going on, our water should also come off, okay, because this step cannot happen unless water comes off. So what we're going to get in the end is palladium with two chlorines connected to it, a hydride on it, and now a ketone that's bound to the palladium in an eta-2 fashion. Okay, so a ketone is bound to the palladium in an eta-2 fashion. And again, throughout all of this, let's make sure we've got all the oxidation states right here. Our charges right. So palladium is still 2 and 2. Okay, so palladium continues in the +2 oxidation state throughout. Now I'm completely out of space here, but I do want to show what happens after this. So from here, another water molecule can come in. Okay, so a water molecule comes in which can displace this ketone product. Okay, so we get a palladium with 2 chloros. There is 1 hydride and water molecule. This is still 1 negative. And from here, I'm completely stuck here. I'm going to probably erase this part. We don't need that. And redraw this a little bit. Okay, let me redraw that here, because what we had was palladium with 4 chlorines, 2 minus. What we had was the alkene coming in, the chloride getting kicked out. So that is what we had. So I just moved it over there. But what happens from here is now, from this step, this palladium, which is still palladium 2, it's in a 2 oxidation state. Some water can come in, and the palladium, which is your solvent, okay, because the palladium, so the next step, what we're going to do is a reductive elimination. So let me show the water on the other side to make some room for myself. So this is reductive elimination. That's the step. So some water comes in. I'm sorry that my board is really small, well, at least small for this mechanism. It's a really long mechanism there, okay? But some water molecule can come in, reductive elimination happens. So reductive elimination is, again, a very standard reaction in organometallic chemistry. And essentially what happens is a metal in a high oxidation state goes down by 2 oxidation states, and it releases some of the ligands around it. Does not have to be all ligands, okay? It does not become like a bare metal or like a naked metal atom, metal like in its 0 oxidation. That does not happen, and it does not have to be 0 oxidation. In this case, it will be a 0 oxidation state. But what happens in reductive elimination is a metal in a higher oxidation state goes down by 2 oxidation state. Since this is palladium 2, when it undergoes reductive elimination, what it does is it will become palladium 0. So palladium plus 2 becomes palladium 0. So palladium was 2 in the plus 2 oxidation state until now. Now it becomes palladium 0. Now, at this point, it's not just palladium 0 by itself. This palladium 0 could be surrounded by some ligands. We're just going to write L, some number of ligands. So we're going to say L and N. And this L could be something as simple as water, or if there is a co-solvent. Sometimes you would notice that in the Wacker oxidation, DMF is used as a solvent, or some other solvents are used. So it could be anything that can coordinate to that metal. Okay, so this L, it could be as simple as a water molecule, so palladium 0, and plus it's going to release HCl. So this H and Cl, they are getting reductively eliminated, and plus it's going to release chloride ions. There was another chloride ion over there. Now, this palladium 0 is what's oxidized by the copper, because if this palladium 0 cannot go back to palladium 2, you will not have a catalytic cycle, which is what we basically developed over here. So to make this catalytic, what happens is the copper 2 chloride, it's a well-known reductant, oxidant for palladium 0. Sorry, I must have like misspoken like earlier. So the copper 2 chloride, it oxidizes Yeah, sorry. It is a well-known oxidant for palladium zero. I think I just misspoke right now. So it is a well-known oxidant for palladium zero. The copper 2 chloride will get reduced to copper 1 chloride. And again, in this process, you're going to release some chloride ion because there were 2 here, and so you get 1 out there. Okay, you're going to release chloride ion. And so the copper 2 chloride oxidizes the palladium 0 to palladium 2. And now you can work on the stoichiometry as to how many copper 2s you need to oxidize. Sorry, I think I misspoke again. But copper 2 oxidizes palladium 0 to palladium 2 oxidation state. You will need 2 copper 2s for each palladium 0 to be oxidized. And as mentioned earlier, the copper 1 chloride can be oxidized back to copper chloride, copper 2 chloride, using oxygen. So that's why you need the air. So the oxygen oxidizes the copper 2 chloride to, sorry, copper 1 chloride to the copper 2 chloride. And so that's where you have like a fully catalytic process, and the terminal oxidant that you're using here is oxygen molecule. For lack of space, I don't want to go into details over there, but that's the mechanism of a Wacker oxidation. So the palladium continues in a +2 oxidation state throughout the mechanism. In the end, it gets reduced, okay? And like I said, over here, this enol, if this were to dissociate from the metal and tautomerize to our product, which actually is formed over here. I forgot to write the product here. So this is where the product would be formed. So the water molecule comes in and it displaces the product, which is the ketone. So if this enol were to basically dissociate from the metal at this point and tautomerize independent of this metal in solution, then this ketone product that's formed, it should acquire some hydrogens from the solvent, which does not happen in this mechanism. So that's clear evidence that it is a process that basically continues on the metal. So hopefully you find it helpful. Leave me comments. I'll be more than happy to address any questions you have. Thank you.